start recording. Okay, so second book, just for documentation purposes. So I'm gonna read, or well, at least we're gonna attempt to read, Category Theory for Programmers by, how do you pronounce his name? Bartos? Bartos?
I want to say it's Bartos, but I don't know how to pronounce his name either. That's just a guess.
Cool. So we read the first three chapters, and we're gonna talk about it. And this time around, I'm actually gonna, sorry, I'm gonna put on the screen the stuff as we go forward. So let's go to part one, the essence
Uh,
of composition. Go.
and just FYI, for the sake of record, uh, there's actually a version of this book available on GitHub.
Oh yeah, there's a version of that.
Yeah, just wanted to point that out.
Sure. Okay, so let's go. So apparently a category is a bunch of objects and a bunch of arrows. And the author made very explicit that we don't care about what are within the objects, right? We only care about the arrows among them. Uh, so that's basically the essence of a category, apparently. And we're gonna call the arrows morphisms, right? So if you have a morphism from A to B and a B to C, we're gonna talk a little about a little bit later. But to have a category, you need to be able to be composable, right? So you should be able to make a composition A to C if you have A to B and B to C, which is
Yeah.
very, very cool. So this is the notation, and when using this guy here, we read from the right to left, so a little bit of a Japanese touch. So
No,
you
no, no.
first,
It's not Japanese. It's not Japanese.
I'm pretty
Because,
sure it is.
no, no. Because in Japanese, you read from top to bottom first, and
But
then the next line is on the left.
top to bottom, but there is no notion of height. So the right, I meant right to left, as you read like a manga or something.
No, no. But the reason it's like that is because Japanese and Chinese as well, they were written on scrolls. So you hold the scroll on your left hand, and then you pull on it with your right to unroll it. And as you unroll a line, it is written from top to bottom. And then when you pull a little more, the next line will come out on the left.
You mean like a scroll like this?
Yeah, except you are holding it wrong. It's actually rotated 90 degrees. And in fact, there
Wait,
is
you open with
actually,
your right hand, you said?
yeah, you hold the bulk of the scroll rolled up in your left hand.
Yes.
Then you take the flap with your right and you pull on it.
Okay.
And the first line will be written vertically from top to bottom.
Oh, now it makes sense. It is written vertically. Okay, I forgot about that. Cool.
And yeah, and as you pull, the next lines will appear on the left. But the conventional way to convert that to read like lines one on top of the other, the way
Hmm.
we do with English, is actually to just rotate the entire thing by 90 degrees. So it turns out that reading Japanese, printed Japanese, is basically like reading English, left to right, top to bottom, no difference.
Wait, you said you grab this and you rotate 90 degrees like this?
The other way around, the scroll goes on the bottom.
So here.
Yes. So you
Ah.
pull upwards. The first line will appear
Ah, it is
at the
left to
top.
right. Okay, I never thought about that. Anyway,
Yeah.
that's a parenthesis. Let's continue here because we have three chapters to go about. And then we're gonna read this as G after F, right? So this is very common sense for functional programmers. So threading macros, Haskell's dot operator, whatever this is called in Nekoma and F sharp, pipe in Bash, all of those things they have the same kind of like notion of one thing after the other, which basically
Yeah.
means this.
Yeah, it's just that some of them are right to left and others are left to right, but
Yeah.
the meaning is the same.
So this is Haskell notation, which is very similar to this notation, but you can do it in other languages as well. So here are the properties of composition, which is very, very important, that any category must satisfy. So the first thing is that it needs to be associative, which means that doing this or this should be the same, right? So if you
Right.
compose the first true or the last true, and then you do the remaining one, it should be exactly the same. Um we should have an identity, so like a morphism that goes from the object to itself. And if you compose another morphism with identity, you should have the output should be the morphism alone, and vice
Yep.
versa for going. So f after id or id after f, they are all equal to f. So the author also wants you to understand that this can be done in other languages. So we have a little bit of the C++ templates here. This is how you do identity in Haskell. So here is how we can, and again, this is pseudo Haskell because of because you cannot define well, it's not natural to define equality of functions. The previous book that we read, there was a notion of equality of functions.
Yeah, but
Uh,
that's because it was a Lisp book and the functions were actually just normal data structure. So you can just look at the body of the function, and if the body is the same, you say the function is the same. Of course, that doesn't take into account if two functions have different bodies but exhibit the same behavior.
yeah,
But that's like solving the halting problem. You can't really have that.
yeah, but this is pseudo Haskell because it is just like because of this equals equals here. No big deal. So then we go to composition as the essence of programming. I believe that he's talking about that you can do a lot of many things. Yeah, the composition, right? So you have a big problem and you slice it, so you have smaller problems, and then you compose them together to have the final solution. Um, and we do that not only because it is organized and structured, but because that's the way that our brains work. We cannot handle too much information at a time, right? So the very classic example is trying to understand how a wave breaks, looking at the level of particles of the water, right? Nobody will ever be able to comprehend and understand how a wave breaks from that point of view. You need to abstract things out to have less moving parts in order to make the solution. And we do that in
Yep.
programming as well many times. Uh, so then category theory apparently is all about that as well.
Yeah,
Uh,
composition.
yeah,
It's the
and that's
soul of category theory.
that's the end of chapter one. So now types and functions. So this is a little bit of like a prelude because this is not like chapter three is more focused on category like starting category theory per se. This is more like an introduction to some pieces that we need to know. Uh, uh, oh, okay. So this is the monkey problem. Okay, so it's talking about like making a hypothetical experiment of having many monkeys trying to randomly create a program that works as intended. And if we have a type checker, that's going to take a lot more time, right? Because they're going to have to also please the type checker. Yeah,
Yeah.
so in dynamically typed languages, type mismatches will be discovered at runtime, eliminating a lot of correct problems before they have a chance to run. Yeah, so in the because he's basically talking about like strong versus weak, static versus dynamic typing, and the monkeys would have a better chance if the program uh, was able to run at all if it was statically typed, because then you can filter out a lot of the nonsense first. Um, Types are about composability. I already forgot what this is talking about. Oh, it's talking about type inference. The stronger. Okay, so this is still talking about strong typing slash static typing. It is saying that in Haskell, type annotations are purely optional, which is true. But I don't like it. I am one of the few Haskellers that I actually like to have my type annotations everywhere, because then I don't want the inference to shoot me on the foot later on, because something changed in a function that is calling the other one, and because the other one can still be like more generic, and then the types will still match. But I like to have my type annotations anyway, so I know exactly what this function is doing, and I don't have to read the function, right? I can just look at the type. But I understand that a lot of people like just like type inference, GGs. I understand. Uh,
Yeah, one thing that if you allow someone who prefers dynamic type systems to make a statement here, I wouldn't
you
want
are allowed.
I I wouldn't want to rely entirely on type inference either because here's how I think about it. Uh, Static types are a way to encode the assumptions that your program makes, right?
Yeah.
And
Not only
ideally, you
that,
want
but it's
those
mechanically verified.
as it's a mechanically verifiable way to encode the assumptions that your code makes.
Yes.
Ideally, you want to make your assumptions explicit. So why would you rely on the type inference at the top level where the entry points to your code are? You want to be able to know what assumptions those entry points make, right?
Yeah, no,
So
but that's the
yeah,
thing. You always can retrieve that, but then you have to read what the body of the function is. And that's my problem, because I don't want to read at all. If you have a function that is calling four other functions, and now I have to read four function bodies instead of one, instead of only caring about what is the API of this function, I want to call it, what are the requirements, what's going to be the return. So it to me, the moments in which type inference makes the most amount of difference is when I don't know why the type annotation is not matched in the implementation. When I'm doing something wrong with like state t or st, IOREF, and all that stuff, I use the type inference to guide me to know what is the final type of these pieces, to know where is the missing link that I'm missing, because my type annotation is wrong, and this is the correct one. If you're using LSP, you can actually see what is the type if you remove the type annotation. So then I can see what the type inference is teaching me. It is telling me what is in there. And when I'm doing this refinement phase, I use a lot of type inference. I use a lot of type inference. But once I get it done, I put back the type annotation. So that's how I do it. Okay, so now we're going to talk about what are types, right? So types are sets. No surprise, no surprise. Sets of values, right? So we're going to start by well, not the simplest, but one of the simpler sets, which is bool, in which has only two members of the set, which is true and false. The char is a
um,
set of characters. Go on.
by the way, can I just say that I vehemently disagree with the notion that a set can be infinite?
Uh,
Yeah,
Justify.
because a set is theoretically, at least, it should be a mathematical object, right?
Yeah.
And you should be able to build it, like actually write it out on paper or something. You can't
Mm,
write out an infinite set.
there, nobody said that. You are saying that.
Well, yes, because that's how I look at mathematics.
Oh, so you should be able to touch it?
Not necessarily touch it, but like being able to, because like you wouldn't say that you can touch text on paper, right? But you can at least see it, right?
Um, so for you, the real numbers are not infinite.
For me, the real numbers actually don't exist at all because the way they are typically formalized in theoretical, in pure mathematics, relies on infinitely large objects,
Wait, so you are
which
basically denying the notion of infinity.
I'm not denying the idea that something can be potentially infinite. Like, okay, I have the natural number 0, that's my starting point, and I can get the next natural number by adding 1 to it. Like, typical Peano arithmetic laws that you would see encoded in proof languages or dependently typed languages, I guess. Um,
Sure.
I don't mind saying, okay, here's an initial set of values. Here's an operation that takes a value from that initial set and builds another value. If you have those two things, you can have a potentially unbounded number of values that satisfy that type, right?
That still
But
doesn't
I wouldn't
explain what you said before.
but I wouldn't call that an actual infinite set because you can't ever enumerate all of those possible values.
I don't understand why there is a. I never heard this requirement before. So you should be able to put in a piece of paper the members of the set to enumerate. You should be able to enumerate them, all of them.
Yeah,
Why?
I yeah, I don't think I'm the kind of person who thinks that an actual proper set has to be finite.
But
Like
that
you
doesn't.
have to
But
be able to.
who? Why is this premise there to begin from the
Well,
start? Why?
because my because my the way I do mathematics is colored by my perception of how computers work, right?
But
Because
that's not.
I'm a,
But a computer
and
is
a
an.
computer, but a computer has a finite amount of memory, okay? And any information that you want to store to manipulate has to be either finite or you don't have to look at the entire thing all at once.
Man,
And a set is a thing that you can look in its entirety because it's a value, so it cannot be infinite. It's as simple
yeah,
as
but
that.
you are completely bending one thing on top of the other. You are completely picking one abstraction, which is the computer, which is based on another abstraction, which is a Turing machine, which is, by definition, inside the set of mathematics. And you are reversing the roles, bro. You are saying that mathematics needs to bend its knees for the computer, but it's the complete opposite. Mathematics is much bigger than a computer, much, much larger. You can do a lot more than a computer.
In it, really.
Yeah, because the computer is a tool to try to attempt to solve computations. Mathematics is way broader than that. It's way broader than that. But we can discuss this later. But that's weird. That's the weirdest take I ever heard from you. Yeah, let's continue. So we have a value x that is member of the set integer.
Type, not set,
Yeah, sorry,
because
the type integer, which is the C++ int, and that's fine. So then we're gonna reach the great thing is that there's a category of sets, which is called set, and we will just work with it. So there's a category of sets, which is called set. Uh, okay, so there are sets with one element, right? So one element sets.
yep.
And he's saying here, we for now we have the privilege to know what is within those sets, but ideally we're gonna forget about them a little bit later.
Yeah. Category theory doesn't care about the details. It only cares about how the parts relate to each other.
Yeah. Uh, okay, so now it's gonna talk about bottom, right? So bottom, there are some calculations that have recursion; those might never terminate, right? And we can ban them, right? And that's a problem because we cannot distinguish. We can try to ban them, but we cannot distinguish between them because that's a famous, also well-known Houghton problem. Uh, uh,
I just wanna, as an aside, there are restricted circumstances where it's actually possible to do that, but that severely limits your expressive power, as you may
and I
imagine.
don't think it's
Uh,
general.
no, it's not. It's not fully general. No.
Yeah, so
Um,
you're gonna have to trade
uh,
something.
Famously, one language where it does actually do totality checking is Idris.
Oh, okay, cool. I didn't know that.
Yeah.
Um, so then you're gonna have bottom, right? Which is the idea of in like you can think of a bottom of many ways: non-termination, error, exception, something didn't work as expected, bottom. Haskell doesn't have bottom though. It does have the undefined, right? Uh, so then we can say that a function f picks a bool, and so bottom is the member of all sets, basically. Uh,
Uh, Equivalently, you could say that bottom is the subtype of every other type.
yeah, I guess so. Which is a member of any type. You can write. Uh, okay, now he's talking about functions being partial functions, right? Which is when you have values on the domain that are not being mapped to the codomain. And when that happens to every single member of the domain, we have total functions. Um, so because of the difference of bottom, we will see that the category of Haskell types and functions, we're going to refer to them as Hask instead of set, right? Uh,
Right, because we have to deal with non-termination somehow.
yeah. It's okay to ignore non-terminating functions in bottoms and treat Haskell as set. Why do we need a mathematical model? Okay, so this is very interesting. So why do we care about all of this? Because there's a bunch of things that the mathematicians can do that we can't. They have some properties. They have some invariants that we care a lot about, and we would like to bring those over to programming because we are jealous fundamentally. And then we're gonna try to be inspired by those folks and try to retrieve some of the properties that they have there. So he's talking about operational semantics. There's a whole thing about axiomatic definition of programming languages, the denotational semantics, operational semantics, and all that stuff. Uh, but we want some sort of, I'm not gonna say formalism, but we want some structure to on how to do programming, so that we can reason about it better, right? We can reason about it better. Uh, so then he's talking about that. So here's the alternative, the notational semantics, and it's based on math. So we basically the notational semantics in a nutshell is that we're gonna try to separate the creation, like the construction of the syntax, from the meaning of those tokens. And the meaning of those tokens usually is attached to a mathematical interpretation. And then if you want to prove a property of a program, you're basically proving a mathematical theorem, right? And just as a side note, a lot of theorems are not um, they are very abstract. You can try to put them in like a piece of paper, but they are very abstract things. Um, so you have an example here. So factorial is a product from this is creating a list using a range. So this is 1 until n, and you're gonna multiply all of them using product, right?
Yeah, the n is included in the list. That's terrible.
The n you said
Yeah,
the n is included in the list. I'm confused. Why is that a problem?
it's a problem because if you want to deal with ranges of natural numbers elegantly, you should include the lower bound because otherwise it's very awkward to talk about a range that includes 0, which is the smallest natural number. And you should not include the upper bound because if you include both bounds, then you can't really talk about empty sequences at all.
If you put one dot dot, oh no, that's not going to be empty. I see. That's a weird complaint, but fair. Uh,
It's a complaint straight from Dijkstra, actually.
no, yeah, I understand that some people would complain about that, but I never thought about that like that. So this is the C version of this program here. and then he goes abroad in some other example. So what's the mathematical model for reading a character of the keyboard and sending a packet across the network? What is the mathematical model for a plane that is flying across the sky? Though not everything is easily, um, we're not going to easily model everything in a mathematical way.
Well, there is the actor model if you want to go there.
uh, I don't think this is what the author is talking about. He's talking about model checking, right?
But
So
it is a model.
yeah, no, but it's a different, it's ambiguity. So model checking there. So it's a method of checking whether a finite state model of a system meets a given specification. And I think this is an elevator. Yeah. So this is a problem that we cannot model check every single thing on Earth, which basically means that we're gonna have some ad hoc stuff at some point. Until now, it is kind of unavoidable. Um, so he's talking about that we can have perform formal proofs of correctness about software.
Monads
Um,
mentioned.
yeah, no, the monad is mentioned here, right? So that apparently the notational semantics received a new lease of life and made pure functional programs usable because of monads. But it's going to talk about that later. So we're going to talk about that later as well.
Yeah, I'm not a big fan of monads.
I am
I
a big
like
fan
the
of
fact
monads. I am.
the problem with monads is that it's very difficult to mix different monads together. They don't compose very well.
I never had this problem. I already had a stack of transformers on top of each other, and I never had a difficulty type checking them. But many
No, the
people
problem is
complain
that you
about
have
that.
no. The problem is that you have to have the stack of. The problem actually is that you need the stack at all. That's the problem. You have to define, okay, in which order am I composing these things? That's not actually ideal.
I agree that the fact that they do not compose in a seamless manner is not ideal. But I would say that discarding the idea of monads because of that is a bad move. It's
No,
a
I'm
very
not
bad
going to
move.
say I'm not saying to discard monads. I'm saying you shouldn't use them as the basis of your effect system. Um,
I would say that
Fun
if you don't have
fact.
algebraic effects, that's the way to go
No,
if you
no,
want
no, no, no,
purity.
no, 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 no. No. Hear me out. The thing about algebraic effects is that it actually built on a monad. It's built on the continuation monad.
Sure. Even then,
So,
if you're not
so
doing that,
my problem is not with the fact that okay, monads don't compose well, so let's not use them. No, they are actually a perfectly fine way to model effects if you just have one. But then the better way to compose multiple effects together is to say, okay, let's take the most general monads possible. Let's use that as the monad. And then the effects will have to be modeled inside of it through some encoding. And that encoding is possible for the continuation monad because it is actually powerful enough to model pretty much all other monads.
yeah, but you're
There's a
losing
result.
you're losing expressiveness doing that.
No, you're not actually.
Yeah, you are. You are grabbing a description of a pattern and jamming them in IO.
No, it's not IO. It's the continuation monad. It's
No,
different.
IO was just an example, but you said the most generic monad, right? But I don't want to fit something else onto the most generic monad available. I want to have this. This is the perfect description of my problem. And I don't want to jam it just to fit on it. I
No, it's not a
understand.
gem. It's an encoding. It's slightly different.
Okay, I'm using jam kind of loosely defined. It's an encoding, sure, but you see that there's gonna be some translation happening between what this was supposed to be, and then what is end up being, right?
Ah, look, I think we can save this discussion up for later because it's going into another tangent. But have you actually looked at? Remember when I linked the Kislyov website? Have you
Yes,
looked into that at all?
I looked into it, but maybe not the one that we are talking about right now.
Yeah, there's a section there dedicated to effects actually, and it's very interesting. And it talks about precisely this very problem. Um,
Okay, I can take a look on that later.
yeah,
Uh, sure. So pure and dirty function. Okay, so now this we're talking about side effects. We're talking about that math, they don't have a notion of side effects. We do, and because of that, we don't have some invariants and some properties that they do, the pure guys.
Can I just say that I really like Scheme for the fact that it doesn't call its notion of, you know how you grab a piece of code and you give it a name? In Scheme, that's called a procedure because it's not pure, so it's not a function.
Yeah, no, I
Uh,
like when we have that distinction of procedures and functions. I do like that. But then he's just explaining that if you have a function that given an input, you always get the same output with no side effects. We're gonna call those pure functions. Um, and the key part of no side effects. That's very important. Uh, and what is a side effect? Maybe people don't know what that is. A side effect is when you're doing something in the real world. Let's say like that. So something is happening here. So I have a server running, and it's an HTTP server of sorts, and my function is doing retrieving information from the server using an HTTP request, right? So the way that I like to imagine this is that imagine that you're writing a program in a piece of paper, as we would do in math. A side effect is the paper having access to the information that is outside of the paper. So, so we're talking about like databases. We're talking about exceptions. We're talking about the energy shutting off, and the computer is now off. We're talking about the notion that there is a state of the world, so things in a state, and you are
uh,
poking this state that outside of the paper, and you're retrieving information from that and doing something about it. So that's the way that I like to imagine, that I like to see it.
I really like the definition that Kixilov gives, which is based on another earlier definition from Felicin, which is um, an effect is basically an interaction between the running program and the environment the program is running in.
That's cool. That's also a good definition.
And fun fact, by that definition, if you try to encode first-class functions as an effect, constructing a function is effectful.
Yeah, yeah. Let's go a little bit faster here because we have chapter 3 also. So then we have the void in Haskell, which is basically the set that you cannot instantiate, right?
Yeah, it's
Uh,
the empty type. It has no elements
yeah. So
whatsoever.
you can define a function with this type signature, but you can never call it because you don't have a member of this set because it's empty, which is very very cool. We also have the singleton set, which is a set with only one element. So this is an example that is like mimicking that idea. So every time you ask f44, it's going to return 44, which is kind of like the only member of the set.
Which makes sense, right? It has only one possible input, so because it's pure, it also can only have one possible output.
Yeah. So we have unit, which is open close parentheses, which is per unit, as he's saying here. Uh, Functions from unit to type A. Yeah, he's basically saying what we just said. Uh, okay, so now he's explaining that if you have functions that return unit, those functions are meant to be used to do side effects, and they are procedures, not real functions in a mathematical sense. A pure
I
function that
mean,
returns
yep,
unit does nothing. It discards its input. Makes sense?
yeah, yeah.
Yeah. Cool. The above can be rewritten as. Okay, so this is basically syntax. And we can also make the unit function that takes whatever and returns units, right? So this is a polymorphic function. The same thing with templates. Then we have the bool with two members here, making as an in C++. Then we're going to have a predicate, which is a function that takes uh, uh, something and returns a boolean. And that's it for chapter 2. So now we're going to talk about, this is the real meat. This is the main entry, the chapter 3. So we're going to talk about some categories, right? So the first one is the one with no objects and no morphisms. It's a very, quote, very sad category. Hilarious. Uh, okay. Simple graphs. Oh, we're gonna talk about a free category, right? So this is where we're gonna. This is a very like intricate process because you need to grab the objects and all the arrows between them and compose all the arrows, and then those will generate more arrows, and then you need to compose those with the even more arrows, generating even more uh, until you have the final graph, which is basically going to be like a tangled mess of morphisms. And apparently, this is called a free category. This is called a
Yeah,
free category.
because yeah, if you have a graph, you can get a category for free. That's why it's called a free category.
Yep.
You just
So
have to fill in the arrows and you're done.
yeah, and then we're going to talk about the pre-order category. So how we're going to check for this? We're going to check if every object is less or than or equal to itself because we need identity. Nice. We're gonna check if they compose. So if A is less than or equal to B, and B is less than or equal to C, A will be less than or equal to C as well. So this is okay, and it is associative. So then we have a pre-order category, and then we have if you add an additional condition, which is that if A less than equals to B and B also, they must be the same element, and that's called a partial order. And if you have if you add another condition that any two objects are in relation with each other, that's total ordering, right?
Very handy to have.
Yeah, very handy. So then we have the pre-order category, and then we're gonna define like this is basically defining some nomenclature like glossary. We have a home set, which is basically means that you have a category C from with a set of morphisms from object A to B. Uh, so that's
Yeah, one way to think about it is okay. So a category is basically you can think about it as a directed graph, right?
yeah,
So from each element, which is a node, if you have a morphism to another element, that's like having an edge, so you can go from one node to the other. A home set is basically saying, okay, here's node A, here's node B. I want to know all of the paths that go from one to the other.
yeah. Pretty much. So why is the pre-order category empty or singleton? Because if you have what is this is what Marinho helped me before. So this is a set of morphisms. It's a set of the arrows. That means that you can only be less than or equal or not nothing, right? Which
Yeah, because
basically
that's the only
means
arrow.
this.
Nah, yeah.
Um, so that's pretty much it. So now we're going to talk about monoids. So very, very, very interesting, but people are afraid of words. So some people are confuse monoids with monads, but they are not. They have a relationship, but they are not the same thing. And monoids is very, very simple. Everybody worked with monoids at some point. So what are they? So the first thing is that to be a monoid, it's a set with a binary operation. So in Haskell we call this operation mapend, right? And this needs to be associative as well.
Terrible
Uh,
name, by the way.
Mapend.
Yeah, just adding M to the beginning of a word. Ah.
I think it's
My
fine.
problem,
Like,
my problem with that name is that M is used as an abbreviation in some contexts for monad, but here it's being used as an abbreviation for monoid.
Not
I
really.
think that's,
Abbreviations for monads are capital M.
but the problem with saying that is that in Haskell, if you have a capital letter to begin with, you it is a type, not a value.
Nope. Let's go. So if
Uh,
I want to fold over monads,
unless,
it's fold M with capital.
oh, the big M goes at the end. I see.
Yep. So this is if you want to do a fold, but you're doing some monadic things along the way. We use this a lot in silverware when we did the language. This saved my life because this is so freaking convenient. This is so convenient. Specifically because a transformer is a monad, which means that I don't have to care about error handling ever. So I just fold it, and if something along the lines of my operation goes wrong, it just bubbles up. Very, very handy. Um,
Okay, I retract my objection then, but I still think it's a bad name because you're literally just adding a letter to a word.
I thought you would pull over like a Natan move and say, why not binary operation?
Because if you just say binary operation, you're not being specific enough.
Sure. So here's this is basically the definition of associativity. So we are going to show a monoid here. So and we need the neutral element, which is in the case of addition being the append is 0. And then yeah, so that means that we have an addition which happens to be commutative. It doesn't have to be, but in this case it is.
A
Uh,
funny way you can think about it is if you have a category with, well, I think this is, well, I think this is kind of what it gets to in the next section. But if you have a category with only one object, then by definition, every arrow is from that object to that object, right?
yes.
Which means that if you look at the Haskell definition, uh, the declaration for, if you look at the class monoids down there, you have m empty, which is just an m, and then you have m append, which is a function that takes two m's and returns another.
Yeah.
And the funny thing is, this matches exactly the well, not quite exactly. If you have a category with only a single element, so in this case it would be called M, that actually matches exactly the identity function and the composition function that you need to define a category.
Wait, repeat the
And it
last
even has
part?
the same, yeah, because like if you have a category with only one element,
Yes.
so you cannot possibly have a function from A to B, right? It will
No.
always be a function
A
from
to A.
A to A.
Yes.
So there's a connection there with monoids because they're both associative, they both have a zero element, and they both deal with like morphisms on objects, except it's just that in the case of a monoid, the morphism always takes the one object because there's no other, right?
Ah, I see. I see. Okay,
Yeah,
I see.
there's a connection there, and later it tells you how to interpret a monoid as a category, but we'll get there. We'll get
Yeah,
there.
yeah, yeah. We get there. So this is the type class in Haskell that you can define empty and mappend for your type. And then there's a very interesting take here, which is that you provide an element of the set. Well, a type did well. How can I put it? This is a type, right? So this is whatever is implemented in the monoid type class. So this. So you provide me a value of that set because this is a type, and I'm going to provide you a function. I'm going to provide you a function, and that's keep this in mind. Keep this in mind. Uh, yeah. So Haskell has this thing here, which is very true, that you don't have certain assurance of the associativity properties in many other properties like applicative, monad. You have to check if your thing is doing the actual what was supposed to be there yourself. Haskell will not verify for you. As far as I
Uh,
can tell, there are languages that do.
Yeah, Idris is one of them.
Yeah.
Basically, any language that has dependent types, you can use it to prove theorems. So you can say, okay, to satisfy this interface, you have to prove this set of theorems about the implementation.
Yeah.
Otherwise, we're going to reject your definition.
Exactly. So here's the string example. So the empty for a string is basically empty string, and the mapend is concatenation. Um, so this is just how to transform things into other things. This is very interesting. So these two things are, I never thought about it, but there is something called extensional equality, um, which basically means that, what is the difference again?
This actually goes back to what we were talking about equality of functions, back when
Oh
we
yeah, that's
mentioned.
true. That's true. That's true.
Yeah, so there's intentional equality, which is actually very easy to compute. Is just look at the syntax that implemented the function. If it's the same for the two of them, they are
Mhm.
equal.
Mhm.
But then there's extensional equality, which is okay, I have these two functions, they have the same behavior in all cases, every time, no exceptions. The problem with extensional equality is that this is often what we mean when we say that two functions are equal, but that's not actually computable because of the halting problem.
Yeah. So it is saying here. So for any two input strings, the outputs of mapend and plus plus in function form, let's say, because this is an operator, are the same. Yeah. So this is different than saying that mapend and this is the same. This would be intentional equality, right?
Yes, they are syntactically equal.
Yeah. Yeah. And function equality with unspecified arguments is described as point free, which is good to know. And this is the C++ template thing that you can use for C++ if you want to.
And can I just say that as someone who comes from Lisp, the syntax for metaprogramming in C++ is absolutely atrocious.
uh, um, there. Okay. Yeah, I agree that this doesn't look good. My GitHub would also hate. Uh, Okay, so this is basically explaining how to read the C++ code. Now it comes the fun, right? Now it comes the fun. Because now we're gonna pick back that interpretation that we just had about the mapend, and we're gonna convert that to a category. So let's start. So it all starts by the notion of adders, right? Which is basically a moving uh, addition will be moving like a needle on a line, right? Um, so let's say,
Yeah.
for instance, that there is an operation adding 5 to every natural number. So it's going to map 0 to 5, 1 to 6, and so on. So now we have a function and we have a set, right? So the set is the set of natural numbers, and the function is this suppose moving or shifting. And how do the adders compose? Easy, because if you have an addition and then you would do more addition, you can compose these two additions into a greater addition, right? So that means that the composition of the function that adds 5 and the function that adds 7 is a function that adds 12. Haha, we can compose these things. Um and there is also a neutral element, right? Because remember, we need identity to compose with our function and do nothing. And regardless of the position, right? So ID after F or F after ID. And that is adding 0. How awesome. Um,
Yeah,
so,
this is what I was talking about the relationship between monoids and categories. Like, for me, it's actually difficult to explain because I have a very intuitive notion of it, but I tried my best.
yeah, try my best. But no, I think this example is very cool. I think this example is very cool. Uh, And then an astute reader might have noticed that the mapping from integers to adders follows the second interpretation of the type signature. It tells us that mappend maps an element of a monoid set to a function acting on that set, right? So the way that I like to think about it is that the first element, so when you have an adder 5, you're basically putting the 5 here, and the 5 is quote unquote waiting for the other element to come, so it's going to be finish the partial application. So this is basically a partial function. No, not a partial function, a partial applied function that peak it waits for an element and returns the output of the first element combined with the second. Cool?
Yep.
Cool. Uh, uh, and then he starts talking about that we should forget about the numbers itself because again we are leaking the objects themselves. Um, uh, and then he's saying that a
I like to
monoid.
mention,
Go.
yeah, a monoid is a single object category, which is what I said earlier. Um, because of course I read the book beforehand, so I already knew this was coming.
Yeah. A monoid is a single object category. And why? Because we are only handling with m's. Right, Marin?
Yeah. You
So this
have
is this
M's and you
image is
have
good though.
arrows.
This
Yeah, just a pig juggling arrows. Very cute.
hilarious.
And I like the mention of string concatenation here because usually when people talk about monoids, the first example that comes to mind is addition, and the second example is multiplication. But
Yes.
I think string concatenation is much more.
No, but he mentioned that. He mentioned here.
No, he did, and he mentions it again. But I think string concatenation is actually a much better example because it shows that a monoid doesn't have to be commutative.
Yeah, yeah. He also talks about that here.
Yeah,
Where is he saying that? There is we passed through it. I
you're
specifically
looking
also.
at it
Oh,
right
here,
now.
here.
It's
Addition is commutative, but commutative is not part of the definition of a monoid.
yeah,
Yeah, that's. I think string concatenation has a very strong argument in favor of it because it means that associativity, composition, identity element. These are the
yeah.
requirements. Yeah, you don't have to be commutative. Yeah. You might ask the question whether every category monoid, a one object category, defines a unique set with binary operator monoids. So that's a very interesting question. So it turns out that we can always extract a set from a single object category. This set is the set of the morphisms. So all the morphisms that are going from M to M, we can extract out. In our case, the adders. Um, and then we're gonna
Yeah,
use the nomenclature that we learned before, which is the home set, right? So this is the monoid category going from objects M to objects M.
which is the only object in
Yes,
the
in this
in the
category.
category.
Yes.
So this is actually the only home set in the category as well, because there are no
Yes.
other objects.
Exactly. Exactly. So the monoidal product of the two set elements is the element corresponding to the composition of the corresponding morphisms. Oh, the product is the outcome. I always get confused because of this. The outcome, the monoidal outcome of the two set elements is the element corresponding to the composition. Yes, but it is still a member of the M uh, set.
Yep.
The composition always exists because the source and the target of these morphisms are the same type, I should say. It is associative. The neutral element is going to form the identity morphism. Uh, and then we're going to go for nitpicking, like morphisms don't have to form a set. In the world of categories, there are things larger than sets. A category in which morphisms between any two objects form a set is called locally small. But we're not going to pay too much attention to that, according to him, to the author. A lot of interesting phenomena in category 3 have their roots in the fact that the elements of a home set can be both as morphisms, which follow the rules of composition, and as points in the set. right? So because we are basically grouping in the set the arrows themselves, right? It's basically
Yep.
the peak functions as first class citizens, right? Because it's literally
Set of
that.
yeah, set of functions. Very It's a very profound idea.
Yeah. So composition of morphisms in M translates into monoidal product in the set. These M's are different. So this is the monoid, and these are the from M to M. And that's it for
Yeah, that's
for
the
chapter
elements.
3. So next time we're gonna talk about chapter 4. I don't know how many chapters we're gonna do from now onwards because maybe the thing's gonna get crazy. You read chapter 4, right? So how hard is it?
Uh it's basically about monads.
Oh yeah.
There's no other way to put it.
Okay,
Yeah.
so no, but is do you think we're gonna have time to talk about chapter 5 as well, or chapter 4 is already big enough?
Chapter 5, let me take a quick look here. Chapter 5 is about I have the PDF open here. Oh, I'm up to chapters. Yeah, I read chapter 5 entirely. Chapter 5 is about
I'm gonna finish the recording now, though.